Hi guys, let's begin our look at the chemistry of acid derivatives, that is carboxylic acid derivatives. First off, functional groups. This page here shows a variety of drugs with the carboxylic acid derivatives highlighted. Actually, the first two, it's actually a carboxylic acid. Here in Zyrtec and Allegra, carboxylic acid, of course. Then we show derivatives. Here we have a methyl ester in Plavix, where we have, instead of the OH group on the carbonyl, we have the O alkyl, with the methyl being the specific alkyl group. Methyl ester. In Flonase, we have an ethyl ester. We can denote these with abbreviations. That's very common for methyl and ethyl. Any larger groups, typically we would draw a line bond, maybe like for a propyl or an isopropyl. We also have here in Flonase a thioester. Now that was not on your functional group list from Organic 1, most likely. A thioester has the sulfur SR group instead of the OR group. Has a regular carbonyl, but then the sulfur. Now the alkyl group, the R group, happens to have an F on it here, but it could just be a methyl or an ethyl like in these two regular esters. Now in biochemistry you will see some thioesters. So I chose an example that included one here. It is a carboxylic acid derivative. Amides. Long name, of course, being a carboxamide, or usually said carboxamide. Carbonyl with nitrogen. The nitrogen can have H's, one alkyl or two. It doesn't matter, they're all amides. Lipitor has a secondary amide, where actually the amine came from aniline. The aniline nitrogen bonded to a carbonyl. It also has a carboxylic acid. Of course, there's also alcohol groups or hydroxyl groups, aromatics. It has the aromatic pyrrole ring, isopropyl group, etc. Then we have the cyano group, or nitrile. Now, most of your carboxylic acid derivatives are going to have a carbonyl, but the nitrile does not. So how is it a acid derivative? Well, all acid derivatives are at the same oxidation state. And in organic, we determine oxidation state by bonds to a more electronegative atom or bonds to hydrogens. And with a carboxylic acid, the carbonyl carbon has 3 bonds to a more electronegative atom. Three bonds to oxygen here, double bond and single bond. Same thing for an ester, 3 bonds to a more electronegative atom. The carbon does of the carbonyl. Thioester, amide. Carbonyl carbon has 2 bonds to oxygen, 1 nitrogen. So it's 3 bonds to a more electronegative atom. But we also have that in the cyano group. The carbon has 3 bonds to nitrogen. So it's at the same oxidation state as a carboxylic acid. It is an acid derivative even though it doesn't have a carbonyl. Now on the other hand, this molecule here has a ketone, Flonase, and you see that this carbon only has 2 bonds to a more electronegative atom. That means it is at a different oxidation state. And to go from a carboxylic acid to a ketone requires redox chemistry. More specifically, it requires a reduction. Because we go from 3 bonds to oxygen to only 2 bonds to oxygen of the carbonyl carbon, or the main carbon of the functional group. All right. And so it's not considered a carboxylic acid derivative. Aldehydes and ketones are not carboxylic acid derivatives. We will cover the chemistry of those two functional groups during test 4. The chemistry of aldehydes and ketones is a good bit different than the chemistry of acid derivatives. Largely because acid derivatives ultimately contain a leaving group on the carbonyl carbon. Where aldehydes and ketones do not. But we can do some leaving group chemistry. Stay tuned to that. Okay, a little bit of overview there, intro to the functional groups. Thioester being new to most of you. Okay, the nomenclature of carboxylic acid derivatives is covered by separate video, this page here. So I'll let you refer to that video. There are a couple of specialized points to make, some common names, etc. Please look at the acid derivative nomenclature in the other video, the nomenclature video section. Okay, we also have the idea of these omega acids, omega-3, omega-6, omega-9. Please make sure you understand what that terminology refers to. What is an omega-6 fatty acid, etc. That's an important sort of application or it's nomenclature that you will hear out in the real world, if we want to say. As beyond just a chemistry context, but in a sort of a health-related context. Here's a nice amide example, LSD. I'd be interested to read about that historically and well-known amide. The main topic in this video, though, to begin with, let's look at the acidity of phenols and carboxylic acids. Now, it's common to just look at carboxylic acids, but at the same time, we're also going to look at the acidity of phenols because the information sort of goes hand in hand. It's also a good time for us to review some of our acid-base chemistry from Organic 1. Certainly, carboxylic acids are one of the most common organic acids. Okay, let's get into this. I'll give you some pKa's. Alcohol has a pK of about 16. It's similar to water, if you remember. Phenols are more acidic than alcohols. pK of about 10. Phenol itself is 9.95. This pKa can vary greatly depending on the substituents on the benzene ring, and we'll talk about that. And then a carboxylic acid is typically about 4 to 5, even more acidic than a phenol. We need to understand the trend here. Why? Well, as we learned in Organic 1, we need to look at the conjugate bases and assess the stability of those. The conjugate base of an alcohol is the alkoxide. Conjugate base of a phenol is the phenoxide. The alkoxide here is a localized anion, okay? No resonance. The negative is sitting on the oxygen. It is not delocalized. In phenol, in the phenoxide, however, the charge is delocalized. We can illustrate this by showing resonance. Electrons here, pi bond out. I don't really have my pi bond drawn precisely there, but that would lead to this. Then we would have other resonance structures. You should be able to draw them, of course. In the end, we see that this anion is resonance delocalized. That makes it more stable than the non-resonance delocalized anion here, and thus phenol is more willing to become an anion than the alcohol. Now the carboxylic acid, if we look at the conjugate base, we see this anion. We can only draw one resonance structure. All right. Let's circle these electrons. These electrons move in here, and these move up to give this structure here. Same thing over there. And so while there's only two resonance structures that you can show here, importantly, the second resonance structure we drew here, we delocalized the charge onto another oxygen. And that is a much greater stabilizing effect than delocalizing the charge onto other carbons. And so even though you can draw more than two resonance structures for the phenoxide anion, you are not delocalizing the charge to another oxygen, or for that matter nitrogen or any other electronegative atom. You're delocalizing it to carbon. But with the carboxylate anion, you are delocalizing it to another oxygen. That makes it much more stable than this, and thus the carboxylic acid is much more acidic than the phenol. Now, practical consequences of these acidity trends: an alcohol is not going to be stable in any aqueous base by deprotonation. Typically, we talk about converting things to anions, and we can make them soluble in water. You are not going to deprotonate an alcohol using an aqueous base. All right, you should know that based upon pK of 16. And I will illustrate that as a review. If we react this with hydroxide, which is the strongest base you can have under aqueous conditions, I'm not going to show a mechanism here, but that would give this plus water. But that is an equilibrium. And which side is favored? Alcohol is 16, water is 16, and we see that neither side is favored. It's really a perfect equilibrium. But as I've said before, in practice, you need a pKa difference of about 2 to 3 to be practically significant. I'm not going to try to explain that further. A 1-to-1 ratio is no good. Happens to do with phases. Okay, we're talking about two phases, and once you have two phases, you have two equilibria, really. And there it gets complex. A 1-to-1 is no good. But if you react phenol with hydroxide, you would get the phenoxide plus water. That would be 10 and 16. Weaker acid favored would be water. You would see that this reaction would be favored by 10 to the 6th, and thus the phenol is soluble in aqueous sodium hydroxide because it's going to be converted to the phenoxide water-soluble anion. Now, of course, you would thus expect that a carboxylic acid is going to be also converted to the anion, and the anion would thus be soluble in hydroxide as well. We can note that carboxylic acids are also soluble in bicarbonate. which is a weaker base than hydroxide. Now, I'm not going to discuss the use of bicarbonate. You can look at that. You should. Ask any questions. But the main point here is phenols are not soluble in bicarbonate typically, but carboxylic acids are. Thus, we really have shown how we can separate these three using different bases. Okay, let's look at the effect of substituents on the acidity of phenols and benzoic acids. That is, we have an aromatic ring. What is the effect of substituents? Well, if you have a net electron donating group on your phenol, that's going to make the phenol less acidic. It will increase the pKa. If you have a net electron withdrawing group on the phenol, that will make it more acidic and lower the pKa. This should make sense. We're looking at stabilizing the anion here. How do you stabilize an anion? You pull electrons away. Okay? Like here. If the group is a net withdrawer, it's going to stabilize the anion that's formed in the ring. It's going to make that anion more likely to form, and thus the phenol is more acidic. If you have an anion but you have a donating group that does not stabilize the anion, it destabilizes it. It makes the phenol less willing to become the anion. It makes the phenol less acidic. This is the same trend for benzoic acids. Okay? Let's look at some examples of this. If you put a methoxy group para to the OH, the pKa goes from 9.95 with no group to 10.2. The methoxy has made the phenol less acidic. That's because, what do we know about the electronic properties of a methoxide group on a benzene ring? Okay, if we can remember from our EAS discussion, it's group 1. It is a net electron donating group. And we would expect a lower pKa. On the other hand, if we have a para-nitro group, and the nitro we know is a net electron withdrawing group, you see the pKa gets much lower. It is, the phenol is more acidic now than when the nitro group was not there. Now, there's actually a significant drop of about almost 3 pKa units where this only slightly rose. That's because the nitro group is really a powerful electron withdrawing group. It withdraws both by induction and resonance. So this is a significant drop. Now actually, if you put 3 nitro groups on phenol, and in this case they're either ortho or para, this compound, which is by the way called picric acid, I've mentioned it before, it's actually explosive, pKa of 0.38. That phenol is more acidic than most carboxylic acids. That's because of the 3 strong electron withdrawing groups. We can draw resonance here of the anion not only into the ring, but also into each nitro group. You should look at that for practice, drawing such resonance structures. Now let's compare this molecule to the para. Metanitrophenol, not quite as acidic. That's because here it withdraws inductively, but not by resonance. I'm talking about resonance involving the oxygen lone pair. Now in the back there are some example problems for you to be working as homework to kind of show these resonance structures here to prove and to illustrate why this isomer is more acidic than this isomer. Benzoic acids, I'm showing them here with R groups, and the R groups are defined here. If it's hydrogen, benzoic acid has pKa of 4.2. If it's a bromine, more acidic, because the bromine is a net withdrawing group, yeah. If it's paramethoxy, it's actually less acidic, because that's a net donating group. But look at this example here. We have a methoxy on the benzoic acid. If it wasn't there, it's 4.2. If it's there, it's 4.1. The methoxy group has made the acid more acidic. How is that the case? Well, first off, believe the data. I wouldn't be giving you anything false here, or at least I'm telling you it is true, accurate information. Since this is more acidic, what does that tell you about what the group is doing? Okay? It's acting as a net electron withdrawing group. How can it act as a net electron withdrawer? Well, oxygen is more electronegative than carbon. Induction is more significant than resonance donation. Or I should have said inductive withdrawal is more significant here than resonance donation. The oxygen lone pair can donate to the ring here, but it cannot donate to the carbonyl. If it was ortho or para, the lone pair of the oxygen could donate to the carbonyl by resonance. But in this case it cannot. And the major effect is thus, apparently because it's it's more acidic than if there was no group there at all, it's acting as a net electron withdrawing group. The only way it can act as a net electron withdrawer is for we to consider the inductive withdrawing, because oxygen is more electronegative than carbon. Need to draw resonance structures. Let's look at acidity of aliphatic carboxylic acids. Aliphatic meaning saturated. Now, of course, the functional group itself has 1 degree of unsaturation, but we're referring to sort of the R group, the side chain here. We do not have an unsaturated aromatic ring. Acetic acid is the most common example. It has a pKa of 4.76. If we put a chlorine on that carbon, it becomes more acidic at 2.86. That is because the chlorine is withdrawing. And we're really considering the stability of the conjugate base, right? That's a negative. The presence of the chlorine is going to stabilize this negative charge, making the original acid more willing to act as an acid. If we put 2 chlorines there, we've got twice the effect. The compound becomes even more acidic. If we put 3 chlorines, and you can show it condensed, sometimes shown like that, even more acidic. We can compare these two. If the chlorine is removed away from the carbonyl, away from the acidic site, the more it's removed, the less effect it has. And so this molecule, this carboxylic acid, is not as acidic as this one was. But it is more acidic than if there was no halogen out there at all. We can compare the one with the chlorine to an iodine. Why don't you look at these two for homework and predict if they're less acidic or more acidic than acetic acid or this example. Okay, basically compare these to these up here. Probably want to compare it to the one with the chlorine, but whatever makes most sense. Ultimately, what we're looking at is if you have a net electron withdrawing group out here, it's going to make the carboxylic acid more acidic because this withdraws. We can pull electrons away, electron density away from this anion that would form. But if we have a donating group, the anion that would form here upon this acting as an acid would be destabilized if this is a net donating group. Okay, while we're looking at acidity, we can also look at basicity of anilines, because we can consider how groups on the ring of an aniline affect the basicity. First off, an aniline is not that basic to begin with. In an organic 1, we almost said it's not basic because the lone pair is in a p orbital. It actually has slight acidity, and we'll call it weakly basic. Because yes, it's conjugated. But the conjugation is with other carbons. And so if you draw resonance structures, you're delocalizing the electron density onto carbon. And that carbon is like, hey, hold on, I don't really want this electron density. So while it is officially delocalized, it's not delocalized to a significant degree. We've got some gray area there. And because it's sort of gray area, that's why it's weakly basic. Certainly a difference between that and maybe something just like ethylamine, where in ethylamine the lone pair is sp3. It is not delocalized or conjugated at all. Aniline has a pKa of about 4.6, roughly I would say about 5. And we've said that before. Check your pKa table in the back of your lab manual. But you have to be careful. What do we mean pKa? I thought we were talking about this as a base. Well, remember, we don't use pKb's in organic chemistry. Anytime you give a pKa for what is a base, the pKa refers to the conjugate acid. And the conjugate acid here is this guy. After it has acted as a base, it abstracted an H from some acid, and this is what is about 5. Where a regular amine has a pKa of about 10, and that refers to actually the conjugate acid. If you look at these, which one's more acidic? Well, the one with the lower pKa. Since it's more acidic, that means it's more willing to act as an acid and go back to the conjugate base. Okay, equilibrium, but it's more willing to act as an acid. This one is not as willing to act as an acid, so I'm going to draw, it doesn't want to go back here as much. So by contrast, it actually wants to come this way more. So this one's more acidic, wants to go back here. Well, which one of these is more basic? Which one wants to come to the right more? Well, this one up here. We know that from structure because it's a non-delocalized lone pair. It should be more basic. It's more willing and it wants to exist more towards the right. Okay. The more acidic this is, the less basic the aniline is. That's pretty much what we just said. Okay. Need to get these numbers straight. I reckon I had this drawn so I could refer to it. Instead I drew a new one up there and I put an ethyl where here we have a butylamine. Okay. Now if we have groups on the aniline, it's the same as, or maybe it's reversed. Let's see. Electron withdrawing group. Is that going to make this lone pair more basic or less? Well, if we pull this lone pair this way, either by induction or really by resonance, it's going to decrease the electron density here. It's going to make it a weaker base. Less basic, thus lower pKa. If we donate, that's going to increase the electron density here. That would make it more basic and higher pKa. So for homework, look at these and answer, do you expect these to be more or less basic than just aniline itself? Now, we can note that aniline can also theoretically act as an acid. That is, instead of taking on an H, like we did up here, it can actually donate an H, although I hate that terminology. It can let some base take an H, and that would generate a nitrogen anion. Now that equilibrium has a pKa of about 28. Again, check your pKa table. And 28 is not that acidic. All right? But if you have a strong enough base, aniline could serve as an acid. So if anybody ever asks you the pKa for an aniline, you might want to ask him, are we referring to the aniline acting as a base or as an acid? Okay, There's some details here. You're not going to you're not going to know these details unless you spend time thinking about them, questioning yourself, and if there's anything that you're uncertain about, then asking a question to me or look in your textbook. Okay? But the acid-base chemistry we're looking at here is very important. We're also bringing in fundamentals that we have hopefully learned in Organic 1 and perhaps some of the course here in Organic 2. We can also take time to think about extraction process. Okay, how might you separate these 4 compounds by extraction? Please look through here. We can just use acid-base chemistry. For example, there's only one compound up here that would form an anion with sodium bicarbonate. There's only one molecule up here that will form an ion upon reaction with acid. Basically, we can separate things by extraction by getting some compounds to go into the water layer and some compounds to alternatively go into the organic layer. And ultimately, we can get just one compound in one layer. Then we can separate the layers and you will have isolated that one compound from the others. Okay? Again, very important information here that's based upon knowledge of acid-base chemistry. But also based upon our knowledge that ions are more soluble in water typically than neutral organic solvents. Okay. We also have a couple other handouts. And I don't know. I thought there were some resonance sort of homework problems. I must be remembering another handout, maybe one from Organic 1, very similar. Ultimately, let's go back. When we're talking about these things with groups on the benzene ring, you need to be able to draw resonance structures. Okay? Like there, explain this pKa trend or answer by showing resonance structures. Explain the answer here by showing resonance structures, which in this case you may actually see that you cannot draw certain resonance structures, and that would be your explanation. Okay? Any of these with groups on the ring. All right, same thing here. Resonance structures. Application there. We mentioned some of these in class, but for the purpose of the video, I'll mention again. Basically, as usual in my handouts, I try to give you some application application of the knowledge or just some sort of interesting or fun applications. This shows that esters are typically quite fragrant, and many of them have kind of fruity smells. Okay. If you ever seen sort of scratch and sniff stickers that sometimes find in like the toy section or meant for kids or something, but you want one that smells like apple, methyl butyrate. You can also kind of check your nomenclature here, see if some of these names make sense. A thioester is also an amide here. Okay. Cyclohexane ring, a benzene ring, isopropyl group. Okay, terminology. But you can read about this drug. Another drug. Okay, guys, we'll leave it there. We have nomenclature and we have some acid-base chemistry. The next video we will be getting into more of the reactions of carboxylic acids. We have the handout here, including this sort of outline here. We'll also have or this kind of flow diagram, but then we have what I call my outline for the chemistry of acid derivatives, more the outline format, and we will begin with synthesis of carboxylic acids, but we will begin with review of previous methods, and that will be over in the other handout where we see review of carboxylic acids. That'll be where we begin. We will then see some new reactions, some new ways to make carboxylic acids. Then we'll move into reactions of carboxylic acids. So please have, I think we have 3 handouts working here. Okay guys, that's video 1.